All right. So when we left off, I was about to give the real definition of the infinity Braille sets. So that's part one. So previously, in lecture one, we gave an alternate definition, right? We said that A is infinity Braille. This is A contained in the bare space, this infinity Braille. If there exists an ordinal gamma and a set S contained, I guess, in gamma, why not? And there exists a formula phi such that A is the set of X in the bare space such that L of S and X satisfy the formula phi of S and X like this. And we called the pair S phi a infinity Braille star code to distinguish it from the real type of code, which we're going to talk about now. So I can write the right thing. Infinity Braille star code. Right, one thing we said on Monday when we talked about this is this definition doesn't really make the reason for the name transparent. Right, an ordinary Braille set has a construction sequence from the basic open sets. You build using complements and countable unions and intersections, and so an infinity Braille code is the same thing, except that we allow well-ordered unions and intersections, and we need to have the code for the whole thing all at once. So the following formalism is a convenient way of saying that, but that's the intuition. So, okay, for Kappa Cardinal, infinite really uncountable, but for Kappa Cardinal, we're going to let L kappa 0 be the propositional, well, it's the language, let's just say, with propositional variables Pn and an omega, and logical connectives, right? We're allowed to negate, we're allowed to take intersections and unions, well, let's just say this way, closed under well-ordered unions and intersections of cardinality less than kappa. In general, we're not requiring kappa to be regular, but I guess it still makes sense if kappa is singular. So that's the language L kappa 0, and then L infinity 0 is just the union, right, over all the kappas. These things, right? And now if we have a element of the Cantor space, we can consider it as a structure in this language. So X in 2 to the omega, is or can be interpreted is a structure in this language. Right, where we say that X satisfies the formula Pn if and only if X of n is 1. X of n is 1. There we go. Right, and so then a formula in this language induces the set of reals that satisfy it. Right? Okay, so to start with, we will say that A contained in 2 to the omega is kappa Braille if there exists a formula phi in L kappa 0 such that A is the set of X in the Cantor space such that X satisfies the formula in that sense. We're also going to call this thing A phi. All right, so that's the definition of A phi in that sense. Now we're going to tweak this in a number of different ways. One way we're going to tweak it is that we don't really want to talk about the Cantor space. We want to talk about the bare space. That's not really a problem, right? We can just replace our PNs with pairs P and M, right? I mean, we need to have, conjunctions that say that our functions are total, right? We can sort of identify omega to the omega as a subset, right, of 2 to the omega cross omega. So to make that all work out, really, we want kappa to be uncountable, so we can insist that the things we're talking about are total functions. Okay, what we really want to talk about are subsets of omega to the n, like this, but we can sort of take it one more level like that. So there's sort of a level of suppressed coding that lets us talk about subsets of omega to the n as being infinity Borel in this sense. Okay, so now there's one more level of coding. Really, we want to code the sentences in this language with sets of ordinals. So, right. Okay, so using a pairing function on the ordinals, which I'll suppress the details, but function on the ordinals, right, we can code a formula phi, which is in L kappa 0 by a set S contained in kappa like this. Right, so officially, really, the S is our infinity Borel code, right? So in this case, right, is our infinity Borel code for, well, okay, so we'll call this formula when we have S, so it's A phi sub S, right? So phi sub S is the formula coded by S, and then A phi sub S is the subset of whatever product of the bare space that we care about that's coded by that thing. Okay? All right. Okay. And I think I've said what I need to say about that. Let's observe that the infinity Borel sets are trivially closed under complements, right, which the Suslin sets in general are not. Okay. Okay, so I think that's all I need to say about that. Good, so we have two different definitions. We want to know that they're the same, which they are. So, there's a theorem just under ZF, right? So for all A contained in the bare space or whatever, the following are equivalent. Well, there's just two things. So one is there exists an S phi such that A is the set of X, such that L of S and X satisfies phi of S and X, right? And the other one is that there exists an S such that A is the set of X, such that phi X satisfies phi sub S. All right, so these two definitions are the same. Now, one of these two directions is a lot easier than the other, right? 2 goes to 1 is more or less immediate. You have the same S, and there's your formula, right? The other direction takes some work. It's a little bit, well, at least when I did it, it's a little bit ugly. I don't know. Right, for the other, I mean, I'm not going to say much about the details of the other direction, but the other direction can be done recursively. I mean, well, I guess, of course, this is equivalent, right? So it can be done recursively first on gamma and then on phi. It can be done uniformly for all S's at the same time. The restriction of the construction to each individual L of S is in that L of S, right? So when I'm looking in the model L of S like this and trying to, come up with codes for things like this, right? L gamma of S and X satisfies phi of S and X. I have a uniform procedure for turning that into the S prime that codes the same set. Of course, the L of S doesn't see all the reals, right? So it's doing this without seeing the things that it applies to, right? But nonetheless, it can all be done recursively. I mean, that's more or less all I want to say about it. I mean, you have to have an expanded language with some additional predicates and a normal form. One thing to say, I guess, is in this case, the S prime, I think it is contained in gamma plus. I think you, in some case, might have to go up to gamma plus, but that's the worst that happens. Okay, right. So again, there's this procedure that takes you from this S phi to this S prime, such that, okay, I guess it's clear what I mean. All right, so a couple observations about this. First of all, the infinity Borel sets are not literally the same, are not always the same as the smallest class containing the basic open sets enclosed under well-ordered unions and intersections, right? So in general, it can happen, right? It is consistent that the infinity Borel sets are not closed under well-ordered unions. Right? Because you have to be able to pick the codes, right? If someone gives you a sequence of infinity Borel sets and you want to pick a code for the union, well, you have to be able to pick codes for the individual things, and you can't always do that. Right? So there are models. Of course, we're aiming for models where every set's infinity Borel, so then that's not really an issue in those models, but there are models in which you can have a union of infinity Borel sets that's not infinity Borel. The other thing, which is well, it's sort of the whole point of everything, is that in general, infinity Borel sets cannot in general be uniformized. I mean, that's sort of the theme of the whole series of talks. Right, and even more to the point, I can have a, let's see, I mean, it can be, for instance, that A sub phi of S is non-empty, but A sub phi of S intersect L of S is empty. Right? So you can have the code for a non-empty set and not have any members of it. I mean, the most basic example is just L itself has a code for the set of Cohen reals over L. Right? There aren't any of those in L. Okay. Okay. So there's no uniform way to pick a member of a non-empty infinity Borel set. Okay. So the first thing I wanted to do is, I almost said this. It is going to be important later that we know how to go back and forth definably, eventually. I mean, if we get to it. But this is essential that you can definably translate from codes of one type to codes of the other type. Just because this wasn't the right definition doesn't mean we don't need it. Right? We need both definitions as we go. Okay. So the first thing I want to do is do this proof that infinity Borel codes are local. Okay. I mean, this really isn't the main line, but it sort of completes the thought from the first two lectures, and I promised you a proof in lecture 2 and didn't actually prove anything. So just so we can do a proof, I'll prove this one. I mean, it's kind of a cute proof. I mean, I like it. It's not too bad. Okay. So the proof uses some terminology, some of which I definitely made up, and some of which, well, you'll see. Some of which I probably didn't, but okay. So I'll tell you the theorem eventually after I define a bunch of stuff. So first of all, for A contained in the bare space, I'm going to let delta A be the supremum of the lengths of the pre-will orderings, which are wage below either A or its complement. I don't know if that's a standard term, it's probably not. Delta, what I call delta 1A, which actually Hugh in his talk yesterday called delta 1, I call it delta omega A. Hugh called it delta 1 omega A, maybe that's the official term. That's the sup of the lengths of the pre-will orderings, which are just projective in A. All right, so we're allowed to use any projective formula and allowed to use A positively or negatively. Okay, so to keep track of where I put things. Where did I put the first thing? All right, we will worry about that when I get there. Anyway, I don't need the first thing yet. All right. All right. So a couple facts just about these two things. All right. So one, AD implies that delta A is less than delta omega of A. That actually seems like something that really ought to be really simple to prove. I mean, it just feels like you have a lot more strength here than there, but as far as I know, the proof takes some work to do. Maybe there's... The problem is, you'd like to just glue together all of these guys, but you need to glue them together as a pre-will ordering, and how do you definably do that? So, I mean, the second observation, the second observation may be overkill depending on how squeamish you are about singular cardinals, but AD plus DCR also implies that delta omega of A is a limit of measurable cardinals. Now, okay, so yeah, Andres pointed out that I didn't even tell you that AD implies that omega 1 is measurable. That's Solloway's theorem. It's been mentioned in other talks. You can adapt Solloway's proof to get that this cardinal is measurable. And so in particular, there are regular cardinals in this interval. Okay, so we're just going to let delta star A be the least regular cardinal in this interval. In the interval between delta A and delta omega A, like that, and that may or may not be overkill as far as what we need to do. Okay, and now I can state the theorem. So 3 is the real theorem, which just says, assuming AD plus DCR, if A is infinity Braille, then it is delta star A plus Braille. All right, so there's a code. All right. Yeah, is there? Are you worried about this? No? Okay. That's fine, yeah, that's great. Okay, so there's a code in L sub delta star A plus 0, like that. Okay, so in particular, there's a code that is itself codable by a set projective in the original set. That's the idea. Okay? All right, so that's what we're going to prove. And we're going to prove it using a bunch of terms that I definitely made up. It's Hughes proof, of course, but just to help myself understand it, I introduced the following notation. So 4 cardinals, which I just gave the totally random names, chi B, kappa B, lambda B, and rho B. Okay, so chi B is the least chi such that all infinity Braille sets are chi Braille. Kappa B is the sup of the lengths. Nope, that's right. The sup of the lengths of the sequences, well-ordered sequences of infinity Braille codes for non-empty disjoint sets. And lambda B is the sup of the lengths of the infinity Braille pre-well orderings. The infinity Braille pre-well orderings. And chi B, which I'm really not going to use, but just because you're apt to wonder about it, is the sup of the wage ranks, right? Of the wage ranks. Yeah, well, that makes sense. Yeah, so, yeah, it's the supremum of the lengths of the well-ordered sequences of infinity Braille codes for non-empty disjoint sets, right? So it's important that it's not the sequence of sets, but the sequence of codes, right? So how long a sequence of codes can I make for sets which are infinity Braille, but non-empty and disjoint? This is the sup of the wage ranks of the infinity Braille sets. Okay, so I mean, one aspect of this, you could do this for any point class or any set or whatever. I mean, any set or point class has all sorts of data associated to it, all sorts of ordinals you can assign to that class, right? And as far as I know, there isn't really a systematic analysis that tells you, in general, how all these things relate. Now, for these guys, well, one question is whether there are simple proofs that they are all the same. I mean, that may be true, I'm going to give you some simple proofs that relate them, which sort of go into the proof of part 3 here, but it may be that these are all the same thing and that there's an easy argument to show it. If there is, I don't know what it is, but just a couple notes in that line. One is that under AD plus DCR, well, the following, I mean, they all equal theta if and only if that's a theta. Any of them equal theta if and only if all sets are infinity Braille. Right? Certainly the soup of the wage ranks of the infinity Braille sets is theta if and only if every set is infinity Braille. Right? And you can do similar calculations with the other ones. Okay. AD plus DCR, but using a deeper theorem, right? So there's a harder proof, I think also from AD plus DCR, that in fact says they are all the same. But this actually uses a deeper fact. I mean, it's a fact I mentioned in lecture 1, which was that AD plus DC implies that what? For all lambda less than theta, all subsets of the bare space in L of P lambda are infinity Braille. So in fact, they're all equal to the theta of L of P of chi B in that case. But I mean, this is a fairly difficult theorem to prove. This is sort of the last theorem in a chain of theorems that we're aiming for and probably not going to get to. So there's a deep theorem that says they're all the same, but I don't know if there's a simple theorem, a simple argument to show they're all the same. Okay, but I am going to prove some relationships between them, because they make natural parts of the proof of 3 here. Okay, so chi b is less than or equal to lambda b. All right. I don't know, I'm continuing this numbering or not. Chi b is, that's not chi. Yeah. Chi b is less than or equal to lambda b. This is what I meant to say. Chi b is less than or equal to kappa b. Why? Okay, well, just let phi be. Well, we're going to have the following operation on, so just consider the following operation on L of infinity formulas. So consider the following operation that takes phi to phi star, and the operation is basically we kick everybody out who's not contributing, right? So Pn star is just Pn, and the negation of phi star is just the negation of phi star, like that, so that's not very interesting. The star of a union, if I have alpha in Y, let's say phi alpha, and I do the star of that, that's going to be the union for alpha in X of phi alpha star, where X is what? It's the set of things that we're helping. So it's the set of alpha in Y such that A phi alpha was not contained in the union for beta in Y intersect alpha of A phi beta. Okay, so for each, when I come to a disjunction, right, I kick out everybody who wasn't adding anything when I came to that stage. Right? So anybody who wasn't contributing to the union just gets kicked out. Right, and the same thing the other way, right? So if I have an intersection A and Y phi alpha star, that's going to be the intersection for alpha in Y of phi alpha star, where X is the set of alpha in Y such that A phi alpha now doesn't contain the intersection for beta in Y intersect A of A phi beta, like that. Right, so for the disjunctions also, I kick everybody out who isn't contributing, right? And the whole point is my new formula may be smaller, but it defines the same set, right? Because as I went through, I never made a change that affected who was in or not. Okay, so the point now is that A phi, right, is the same as A phi star, right? But phi star, right, is in L kappa beta of 0, right? Because if I had one of these unions, intersections where I wasn't kicking anybody out, after it's refined, well, then I can turn that into a sequence of codes for disjoint non-empty sets, right? Everybody added somebody new, and so I can just take the thing that they added that's new. Okay? All right, so if you're infinity Borel, you have a code I think this, yeah. I think I said the right thing. Okay. All right. Now, the second step is we're going to show that kappa beta is less than or equal to lambda beta. Okay. All right. So kappa beta, not beta, it's B for Borel. Kappa B is less than or equal to lambda B. Well, if I have such a sequence of codes for disjoint sets, I can just uniformly convert it into a pre-well ordering, right? If I have this sequence of codes, you know, phi alpha, alpha less than whatever, right? Less than gamma like this, and these are, the A phis are disjoint and non-empty. Well, I can uniformly just convert this into a pre-well ordering where I list, you know, for each pair alpha less than beta. Okay, that takes a little bit of work, but it doesn't take any work. But if I have infinity Borel codes for two sets, I can uniformly create an infinity Borel code for the product of them, right? So what do I want? I want the infinity Borel code for the disjunction over alpha less than beta of the products A phi alpha cross A phi beta, like that. All right, and so having done that, I can define, this gives me, in effect, a pre-well ordering, you know, an infinity Borel code for that pre-well ordering of that length. Okay, and is there anything else I want to say about it? I think it's not really so important for us, but if these are each in L eta 0, then I think that the code I get here is in L eta union gamma plus 0, like that. Okay. Okay, so we're going to, these are the elements of the proof when we finally get to it. One more thing, which I think is not directly used in the proof, but just is another argument of the same type. So 5 is that if not every set is infinity Borel, if that's not contained in infinity Borel, then lambda beta is less than theta, right? Well, probably more than one way to show this. I'm going to show it in the way that's useful for the proof. I mean, probably there's an easier proof, but so the argument type is useful, even if I'm making it harder than it has to be. So let's suppose that A, B, yep, that's what I mean. Yeah, I keep saying that. Yeah, that's correct. Yeah, I just like writing beta. It's a fun letter to write, isn't it? Okay, yeah, B. Okay. Yep. Anybody? Over here, it just says that the code I can produce for this pre-well ordering is in this. Well, it doesn't really say the right thing, right? I mean, you don't want, okay, you just want to know what the symbols are. It says disjunction for alpha less than or equal to beta of the sets A phi alpha cross A phi beta with a random stray mark there in the middle of it. Right? I mean, we can produce a code for that, giving us that pre-well ordering. That's all. Lives where? Well, it has a code in this language. Well, it's the propositional language where I'm allowed to take disjunctions. Oh, it just says script L for the language. Eta being something that all of these individual formulas are in. They're all in L, eta 0. Union, gamma being the length of this conjunction, plus, 0, that's all. Okay, so let's suppose that A is not infinity Borel and that P is an infinity Borel pre-will ordering. It's not infinity Borel, and P is an infinity Borel pre-will ordering. Well, then what? Then it can't be that A is wage below P, because being infinity Borel goes down under wage reduction, right? If this is infinity Borel, so if this was wage below it, it would be infinity Borel too. So that means that P, it has to be wage below A or the complement of A, like that. All right. So that means that the length of P, whatever it happens to be, right, is less than, strictly less than delta A, right, which is the soup of those, the lengths of the pre-will orderings that are below A, like that. Okay? And of course, this is less than theta. I mean, for the moment, that's all we care about. We're going to do the same argument again and get what we want out of this. Okay, so, all right. So now let's put all this together. So I think I wrote it before, but I'll just write it again. So I can find my stuff. All right, so this is the theorem. I mean, I already wrote it, but the theorem just says that, again, this is under AD. Am I using DCR? I'm sure I am. AD plus DCR. Right, if A is infinity Borel, then it is delta star A plus Borel. Okay? And so here's the proof. Well, if delta star A happens to be greater than or equal to chi B, then we're done. Then we don't have to do anything, because every infinity Borel set, right, is chi B Borel, like that. So if not, well, there's some infinity Borel set such that when I run the star operation on it, right, I don't end up with a well, okay. If not, there exists some phi such that when I run phi star on it, it contains a disjunction or conjunction of length delta star A, like that, right? When I run this process, I don't always get, right, down below there. Okay, and I can take a minimal example and just chop it off at length delta star A. So what I get out of that, okay, so we get a sequence of formulas, phi alpha, alpha less than delta star A, right? So each phi alpha is in the propositional language where I'm allowed to take disjunction conjunctions of length delta star A, like that, right? Each set is non-empty, like that. The sets are disjoint. Right, since I didn't collapse down into this language, right? There's a disjunction. I mean, there's a disjunction or a conjunction, but in either case, I can thin it out and turn it into a sequence of disjoint sets, like this. So I can turn this into a pre-will ordering, like I did in whatever step 4. So we get out of this a pre-will ordering, which is delta star A plus Borel. Pre-will ordering of length delta star A, right, just like we did over here, and running the same argument again, right? Delta star A again is greater than delta A. Preloading is called P. So P is not wage below either A or its complement, omega omega minus A. Okay, so A is below P. Right? But P is delta star A plus Braille, so A is 2. That's wage below it. Yes? What's that? Why are they all in there? Yeah? Right, okay, so I'm just taking a minimal example, right? There's some formula, it's an infinity Braille code, that when I run the star operation on it, I don't end up with all of my conjunctions and disjunctions of size less than this. Right? Because if I did, then every set that was infinity Braille would be delta star A Braille. Right? Okay. Yeah, that's why I'm using it's regular. And I guess, yeah, the question is whether it's over, I mean, maybe it still works if it's singular, but just in an ugly way. I don't know. But yeah, I'm using it, yeah, you're right. To make it clean like this, I'm using the fact that it's regular. Right. Okay. Is that making sense? Right. I have a set that's infinity Braille, but not delta star A Braille. So I take a code for it. I run the star operation on the code. There's a minimal place in that tree where I didn't crush down to a conjunction or a disjunction of size less than delta star A. Right, so that's a delta star A sequence of codes for sets which are either, well, the intersections are properly shrinking or properly growing. It doesn't really matter. I can uniformly convert it into a delta star A sequence of sets. Maybe I really am using regular. Maybe it's important. Yeah. Right? I took a minimal place, so all the previous formulas, all the formulas in that disjunction, right, are in the language. Well, it's okay, it's measurable, but am I really? Is it important in this? Yeah, it's okay. All right. Right, so I do the star operation, right? There's a minimal spot where I didn't crush down to cardinality below delta star A. That gives me this delta star A sequence, not only the sequence of sets, but the sequence of codes for disjoint sets. I can turn that into a pre-well ordering of length delta star A, which is delta star A plus Braille. It's too long to be wage below A, so A is wage below it, and infinity Braille presses down. So, I mean, delta star A Braille presses down under the wage ordering, so A is delta star A Braille as well. Proof is kind of magic. I mean, you know, linearity is a powerful thing, right? It doesn't give you a lot of room to move, so yeah, the linearity of the wage hierarchy just comes to the rescue at the end and makes everything work. Okay? All right. Now, I mean, that really completes the thought of the first two lectures. All right, so I'm just going to say it again, but I mean, I've said this multiple times, right? But with this in hand, we have, so with the coding lemma now, the coding lemma, we have that AD plus DCR implies that if A is infinity Braille, then it is infinity Braille in L of A and R, right? Just because this delta omega of A, that's not what I meant to write, is less than the theta of L of A and R. Delta omega A is less than the theta of L of A and R. Right, so that code, by the Moskowakis coding lemma, is going to exist in this model, right? Because it's coded by subset of an ordinal below the theta of that model. Okay. And with the theorems of Martin-Steele, the sigma 2-1 scale theorem, and Kekris, finally, we get the theorem that, AD implies that in L of R, every set is infinity Borel. Right? The existence of a non-infinity Borel set is a sigma 2-1 assertion now. Right. I'm sorry. Let me just write this, and then I'll. Set is a sigma 2-1 statement. Okay. Right? Because you just have there's a set, and then you just have to look projectively for the infinity Borel code for the set. Right? So if there's no set infinity Borel code that's projective in your set, then or coded by a set projective in your set, then there's no infinity Borel code at all. Okay? Okay. So that's the end of lecture 2. Yeah, that's probably. Oh, let's see. Maybe I'm gluing two different thoughts together. Let's see. Do I really need AD in this theorem? Well, maybe I'm using Kekris to get DCR for myself, assuming. Yeah, I'm using Kekris. I mean, yeah, right. And your theorem uses AD, isn't it? I mean, I guess maybe I'm not using your theorem in what I'm saying here. Okay. Okay. All right. So that's local codes. The main line of these lectures goes to the notion of strong infinity Borel codes. So that's the next topic. Strong infinity Borel codes. Okay. All right. So we're going to do a similar operation to the star operation, except we're just going to thin infinity Borel codes with a prescribed set of ordinals. So given phi, which is a sentence in L infinity omega, and a set sigma just contained in the ordinals, we're going to let phi restricted to sigma. Well, it's just going to be, we only include things indexed by ordinals in sigma, right? So whatever, Pn restricted to sigma is Pn, and not phi restricted to sigma is not phi restricted to sigma, like this. And when we thin a disjunction, sort of alpha less than gamma, phi alpha restricted to sigma, that's going to be the disjunction for alpha in gamma intersect sigma of phi alpha restricted to sigma, and same thing for the conjunctions. It's not really important that the conjunctions are indexed by an ordinal, just by sets of ordinals. Okay. Alpha in this. Okay. So that's just thinning out a code where we just only use the things indexed by, in a conjunction or a disjunction, we only use the things indexed by members of sigma, like that. All right. Okay. So one thing we can note, just as sort of a warm-up observation about this notion, let's just suppose that I had a formula phi is just some phi of S, which is in L delta 0 for some delta, and let's suppose that X is in 2 to the omega like this, and let's suppose that I take an elementary substructure of L whatever delta plus of S and X like that. Right, this is all choice, in the context of choice now. Right. Then Well, x is going to satisfy phi s, right? If and only if x satisfies phi now s, where I cut down to z intersect delta like that. If I have an elementary substructure, right, and a real that's in the elementary substructure, then, right, the set of ordinals from delta that are from that structure are going to be enough to correctly figure out whether x is in that coded set or not. Okay. But it's not going to be true in general, right, that a phi restricted to z intersect delta is contained in a phi in general. I guess I have s's. Right? I mean, this thing now, in particular, if z is countable, I didn't say that before, but if z is countable, then this thing is really Braille, right? This is a code for an actual Braille set, right? And my shrinking respects complements, right? So if this thing were always true, then I would just be proving that every infinity Braille set was actually Braille, right? Which it's not, okay? All right, so when I cut down, if I cut down in this way in an elementary submodel, then for the reals that I see, right, we figure things out correctly. But for the other reals, we don't necessarily figure it out correctly, right? This set doesn't, this is kind of obvious, right? If you, in which way is it obvious? If I'm taking an intersection, right? I have an intersection of a bunch of sets and I only intersect some of them, right? I'm not going to be necessarily contained in the intersection of all of them, right? Okay, so sort of clear that this thing doesn't have to be contained in that. Okay, but we're looking for big sigmas where it will be contained. Okay, so this is what a strong infinity Braille code is. Okay, so I'll just say this. So let delta be an uncountable cardinal, whatever, and let phi now be a formula in L delta 0, right? We're going to have the following game. So G phi delta is a game where 1 and 2 that's 2. They collaborate just to build a set sigma contained in delta, whatever. I pick the first element, you pick the next element, and so on, right? Countable set, right? We build a sigma that's a countable subset of delta, like that, okay? And then one wins the game if and only if a phi restricted to the set that we built is contained in a phi, right? Which of course doesn't always happen, but that's the game. So one's trying to, in effect, make, well, I don't know if big enough is the right way. Well, one's trying to make this work out. Okay. All right, and now we say that phi is a strong infinity Braille code if one has a winning strategy. Okay. All right, so definition is phi is a strong infinity Braille code if one has a winning strategy in this game in G phi delta. And we're going to make two observations about this. One is that the game is actually of the type that ordinal determinacy applies to. This is sort of our... Good. Okay. All right, so our first observation, so notes, whatever, theorems. So again, this is all due to Hugh, right? This game, so delta determinacy, in the sense that we defined as part of AD+, implies that this game is determined. G phi delta is determined. And the point is what? As we play, as we build sigma, we can continuously build, I mean, sigma is countable, so this thing is a Braille set, right? So as we build sigma, we can continuously build a real coding, a real coding of Braille code for a phi restricted to sigma, right? So continuously build. Continuously build. Sort of in sigma as it's built, build a real coding, a Braille code for a phi restricted to sigma, right? And then the set of codes, right? The set of codes for Braille subsets of the real A phi, right? That's just a set of reals. So that's our A from the definition of ordinal determinacy, right? Again, right? Ordinal determinacy said that games that looked like G delta F pre-image A were determined, right? And our F now is this thing, right? That's taking us from the run of the game to the code for the Braille set. That's what our F looks like. And then our A is just this thing. It's the set of codes for Braille sets which happen to be contained in A phi. Like that. That's okay? That's right, yeah, that's right, yeah. So that's, yeah. So I'm sort of asserting something, and I guess you have the right to complain, that this is continuous, that I can continuously build this code. I mean, really, I can continuously build a countable elementary submodel of L delta plus S containing what I've played and highlighting the things that come from sigma and come from S. And then, in fact, I will have coded the... No. Yeah, that's right. I can't really hear what you're saying, but I mean, yeah. So a high-level way to see it is just as we play, we can sort of take Skolem holes and just sort of code up an elementary substructure of a big enough thing to see the corresponding Braille set that we get here, right? Or we could sort of do it at a lower level and just literally just pick out the pieces. I mean, all we're building is a tree, right? So it's got propositional variables at the end, and it's got countable conjunctions and disjunctions, and all we have to do is keep track of. Yeah. Okay. All right. All right. Yeah. Mm-hmm. Yeah. Right. So, but the thing is, okay, there is a tree in the background, right? I mean, right. But all I have to do is choose the relationships in the tree. I'm not choosing codes for the ordinals, right? Yeah. Oh, I guess you're right. Is that we are just enumerating the ordinals as we go. That's right. So we really are just pulling out the subtree, but indexed by the ordinals as we enumerated them. I mean, the game builds us an enumeration of sigma. Okay. The second observation, and the more important one, well, I guess they're both important. The more important one in the short run is that a set with a strong infinity Braille code is Suslin. Okay, which I wrote somewhere. I'm sure I wrote it somewhere. Good, maybe here. Not there. It is there. Okay, good. All right, so observation 2 is that if delta is an infinite cardinal and phi in L delta 0 is a strong infinity Borel code, then a phi, the set coded by phi, is delta Suslin. And the point is, I mean, the definition is just the following, right? Again, it's a strong infinity Borel code, so we can let sigma be a winning strategy for 1. Winning strategy for 1. So then, well, X is in a phi if and only if there is a run of the game, G, whatever I called it, C delta, according to the strategy sigma, such that X is in a phi restricted to little sigma, where sigma is the result of the play, the result of the game. Okay, and certainly one direction of this just comes from the fact that it's a winning strategy. This direction is just the fact that sigma is a winning strategy. All right, so every run of the game, right, if X is in the set that we coded, well, the set that we coded is contained in the real set, so X is in the real set, right? On the other hand, so the other direction basically requires us, having fixed the strategy for 1, to show that for any X that's really in, that we can play against the strategy to find a code that's really in, right? But if X is really in, what does that mean? That means that each disjunction, it's in one of the sets, and so I can just pick that one to get it in, right? If I'm not in a disjunction, in a conjunction, then I just have to pick the set to get out, right? So at every node of the tree, right, if I have a job to do to ensure that X is in my set, well, as player 2, I can do that. Okay. All right, and then there's just going to be a tree of attempts. I mean, there's a tree behind this, right? It's the tree of what? Tree of attempts to build X, right? Play a run of the game according to sigma, and build the code. I mean, at the same time, right? Build the code for the corresponding set A, sigma restricted to phi, and then A, phi itself, is just the set of things. Is just the projection of that tree. Okay. All right. Okay. So we will take a break in a second. I want to say one last thing, if I can actually find the piece of paper it's written on. Okay. So the theme for the rest of, the main point I wanted to deal with, to illustrate in these talks, is the following. Right? So this is what the rest of the talks are about. So there are ways to turn, let's say, the existence of infinity Borel codes. Not always, of course, because not every infinity Borel set is Suslin, right? Into strong infinity Borel codes. So there are ways that work in certain situations, codes that is, right? Using the two topics we have yet to introduce. One is cone measures, right? The Turing measure. And the other thing is the Vopenka algebra, which I haven't mentioned yet at all. Right, so that's the technique that, the goal was to illustrate in these talks. We'll see how far we get. Right, so the next thing is to talk about cone measures, and there are ultrapowers. Cone measures induce ultrapowers of the universe, which can be well-founded, and which can blow up, and we don't literally just blow up the infinity Borel code into a strong code, but by blowing up the universe and having an infinity Braille code, we can find a strong infinity Braille code using the Pankit algebra. Okay. So that's the goal for what's left. I mean, it's more than 45 minutes. Let's take a 5-minute break now, and then I will start again after that. Thank you. All right. Are you still bothered? You're still bothered by this? Yeah. Maybe we can. Let's see. So what do I want to claim? Let's do this. So I think I can just do. All right. Okay, James, can we start? Okay, I'm going to start. Yeah. Okay, so we have about 20-something minutes to talk about cone measures, I guess. Okay. All right, so we're going to use Martin's theorem and Turing reducibility and equivalence, right? Right. So for x, y in, well, it doesn't really matter what they're in, I guess. 2 to the omega, omega to the omega, right? Xt below y is just x is Turing reducible. To y, and then we have the corresponding notion of equivalence. X is Turing equivalent to y, like this. We also have the notion of a set being Turing invariant. Right? A contained in 2 to the omega is Turing invariant. Right? If for all x in A and for all y equivalent to x, y is also in A. Right? So Martin's theorem tells us that under AD, Turing invariant sets either contain or a disjoint from a cone. Okay, so I'm going to sort of state it this way, but so theorem of Martin says that assuming, well, actually, I'm just going to write it this way. If A contained in the Cantor set is Turing invariant, and sigma is a winning strategy for one player or the other in the game G2A, right? In G2A, like that, then, well, let's see. If sigma is winning for 1, what does that mean? That means that for any play for x, any play x for player 2, which is above sigma, right? X has to be in A, right? And if sigma is winning for 2, then for any x that's Turing above sigma, x is not in A, right? And the reasons in those two cases are basically that in this case, if I play sigma against x, I'm Turing equivalent to x, or in this case, if I play x against sigma, I'm Turing equivalent to x. Okay, so in either case, if I have a winning strategy in this game, right, then, well, in the first case, A contains the cone above the strategy. In the second case, it's disjoint from the cone above the strategy. All right, now, I guess it's not an important observation, but of course, reduction is overkill, right? Your notion of reduction only has to make these two equations true, right? So your notion of reduction only needs 4 functions, one to go from here to there, and there to here, and there to there, and there to there, right? So much weaker, well, stronger notions of reduction, but smaller equivalence relations work in this case. Okay. So now we're going to say, we're just going to let the consequences of this be Turing determinacy. So let Turing determinacy be the statement that for all Turing invariant, A contained in 2 to the omega, there exists whatever an x in 2 to the omega such that either, just the obvious thing, right? For all y Turing above x, y is in A, or for all y Turing above x, y is not in A. And the question is, have I been consistent with my notation? I guess Maybe I have. Okay, so this is Turing determinacy. Now, it's apparently an open question. Well, okay. There's a question what the open question is, but it's actually not clear to me. So here's something I don't know. The Turing determinacy, does it imply countable choice for reals? Does it imply that if I have a countable set of non-empty sets of reals, then, right? Right, so this says what? For all A, I in omega contained in power set of whatever, anything minus the empty set, the product of the AIs is non-empty. Okay, so I don't know if, so maybe the conjecture is supposed to have something like this in it, right? So the question, right? So the question is, does Turing determinacy maybe plus CCR imply AD? Right, AD of course implies, the statement is CCR, right? AD implies CCR for sure, okay? And then I guess the answer, again, this is due to Hugh, right? The answer is yes in L of R and other models. Turing determinacy does, this just saves me from having to write it all the time in what follows, it does imply that omega 1 is measurable, which does imply that, not by itself, with CCR, which does imply that there's no omega 1 sequence of distinct reals. Okay, so we're going to be using that hypothesis. Okay. Good. Okay, so what's important for us is that Turing determinacy implies that the cone measure, right, so, okay, so let's just let mu t, I mean, there are going to be so many mu t's in the talk from now on, I don't know, I mean, I want to call it mu tu or something like this, is the set of A contained in the Turing degrees, where A contains, well, let us say it this way. There exists an X such that for all Y Turing above X, the degree of Y, right, is in A, which is the same thing as saying A contains a Turing cone. Okay, so Martin's theorem implies that mu tu is an ultrafilter on the Turing degrees, and countably with CCR, it's countably complete. Right, so countably complete with CCR. Okay, now sometimes we will actually use it for the actual Turing degrees, but often we use it for equivalence relations that contain the Turing degrees. So I'm just going to call these good for the moment. Well, for these two lectures. So let's just say that an equivalence relation relation E on 2 omega is good if, well, Turing equivalence is contained in E. What else? E is, right, there exists a relation less than or equal to sub E such that E is just by reducibility according to this relation. We want that the preimage of each X is countable. So for all X in the Cantor space, the set of Y such that Y is below. What's that? What does the third line says? That just there exists a binary relation such that E is, oh, what I wrote was not what I meant. Like that. Right? The set of things below any X is countable. And I think there's one extra condition that one needs to make this work. I think it really doesn't matter, because in the case we care about, both conditions are going to be satisfied. So either one of two things. Okay. So condition A is that if x is e below y, then there exists a z which is Turing equal to y, such that x is e below z, or second relation just says if x is e below y, then x plus y is e equivalent to y. I don't know, I'm sort of making a big deal about nothing. We're not, okay, well, oh yeah, sorry. Yeah, I guess maybe it's trivial because I am not using it in the context that I meant. The context that I meant is, it's okay, sorry. So it's certainly true that I'm taking too long on sort of nothing. I guess the point is that Turing reducibility is overkill for Martin's theorem, right? You can write down the weakest notion of reducibility for which Martin's theorem holds, right? And then you want to lift Martin's theorem from the weakest version to super relations of it, right? So you want to know that the cone measure being an ultrafilter for the minimal one lifts up to your larger one, and these are the conditions that make that happen. So you're right that probably what I wrote for Turing equivalence itself is vacuous. That's right. Yeah. I mean, yeah. No, E is the equivalence relation, right? And then I have the less than or equal to that induces the equivalence relation. Comes from an order, yeah. You're right. I'm sort of making too much of this. Here's the punchline of this thing, which is sometimes we're going to use Martin's theorem for Turing reducibility, and sometimes we're going to use it for other orders which satisfy these conditions. So in particular, the relations. So L of Sx equals L of Sy, right? For S contained in the ordinals, this is induced by just the relation x is in L of Sy like this, right? Or the relation sort of Hod sub Sx equals Hod sub Sy. Again, for some S contained in the ordinals, induced by x is in Hod of S sub y are good in this sense. Sorry, this is a little bit scrambled, but this is the whole punchline is just that we can lift Martin's theorem to these relations. That's all I want to get out of this. Well, if x is below y, right? So let's look at it in the case. Yeah. Oh, sorry. Yeah, that one. That's one. Yeah, that's what I meant. Yeah. So maybe when you said it was trivial, that's why you were saying it. Anyway, yeah. I mean, this is a side point. The punchline of all this is over here. Right. Yeah, that's what I want to say. Right. If you're reducible in the bigger sense, then you're equivalent to something in the smaller sense for which you're reducible in the smaller sense. This one? Yeah, maybe. Yeah, that's right. Okay. I'm going to erase everything except for this one sentence, and then the one sentence is that Martin's theorem implies, right, assuming AD, that the cone measures for these relations are ultrafilters. Just these. All right, that's all. Assuming AD, yeah, sure. That's right. Right, assuming AD, these are models of choice, and so they each only have countably many reals. Yeah. Okay. Okay. The whole point is we know Martin's theorem for the Turing degrees, and so we know that for each of these equivalence relations, right, every invariant set contains or is disjoint from a cone with respect to this relation. Okay. Okay. So let's not worry about the rest of that. Okay. Now what we're going to be doing is taking these various measures and taking ultrapowers of, well, sometimes of different structures. So, okay. So assuming, again, Turing determinacy plus CCR, I guess. If I have all of DC, then I can just take the ultrapower of the whole universe by the Turing measure, and that's well-founded, right? If I have DCR and, it's an and sign, and V equals L of A in R, right, where A is just some subset of L of R, it doesn't matter. Well, this implies DC, right, so I can appeal to line 1 in that case. There's a theorem of Solloway, which I'm not going to try to prove right now. The proof is not so long. Maybe I'll say something about it. It just says that if E, with its associated reducibility relation, is a good equivalence relation in the sense that I just said, and, well, so now we have the corresponding ultrafilter for it. So I'm just going to call it mu E, right? And mu E is an ultrafilter, which it is, I guess, according to what I've assumed already. If the ultrapower of V, or the ordinals, whatever, if the ultrapower of the ordinals by mu E is well-founded, then in fact DCR holds. I get DCR back from, I'm not assuming DCR in this, right? So if you take the ultrapower of the ordinals of the universe, whichever, by your good equivalence relation, which happens to have the property that its cone measure is an ultrafilter, right? Then well-foundedness of the ultrapower gives you back DCR in this case, right? The point of which is just that DC omega, DC countable, is a theorem, right? And so well-founded countable trees have rank functions. Your equivalence relation is good in the sense that the preimage of everything, the downward image of everything is countable. So below each x, you can rank, if you have a well-founded tree on the reals, right, then you can definably rank the bit of the tree below any given real and then glue those things together in the ultrapower to rank your tree. Okay, all right. The last theorem in this batch that I wanted to mention is due to Hugh, and it's something that I don't actually know the proof of. Okay. It says the following, so AD plus implies that the ultrapower of V by the Turing measure is well-founded. Okay. So we're not going to be doing that, but okay. So the last thing I want to do, I want to state I just want to state 3 target theorems. Of course, who knows how far we'll actually get in the last lecture. I mean, the first theorem is the main target theorem that I wanted to do in the whole course, and so we'll see if we get to it or not. And then there are some theorems that are along the way which are sort of more... Oh. Let's see. Is that needed? Okay, yeah, that's right. Okay. Okay, so the main target that I wanted to do, which at the very least, hopefully we can say something about, at the very least, hopefully we can sketch the proof and say something about when the hypotheses hold. But, I mean, somehow this was the central goal. So let S be a set of ordinals such that, oh, okay. So for the moment, this is really the star of the show, and this relation here I'm calling less than or equal to sub S, right? And the induced cone measure then is mu sub S for an arbitrary set of ordinals, like that. So let S be a set of ordinals such that mu S is an ultrafilter on ds. So that's the corresponding set of degrees, right? ds, right? Just the degrees, the S degrees in this sense. All right, suppose that when we take the product of the ordinals according to mu S, that this is well-founded, and that the ordinal that we're calling delta infinity S, which is the product of the ordinals omega 2 of L of S and X, according to this measure, is less than theta. And we're going to suppose that determinacy holds for that ordinal. So delta infinity S, I don't write the word ordinal. Determinacy is the word I have to write. Determinacy holds. Okay. Then all right, so then if S is an infinity Borel code for set A contained in the Baire space, then A has a strong infinity Borel code contained in delta infinity S, which is definable from S. I hope I've said it right. Okay, so presuming I've said this correctly, this is our way of lifting infinity Borel codes to strong infinity Borel codes, which in turn are Suslin representations. Right? So we want to analyze which infinity Borel sets are Suslin, right? And that amounts to analyzing a certain ultrapower, right? And if we have the right amount of ordinal determinacy, right? Then, well, I mean, it's going to take a little work to say what the strong infinity Borel code is. It's not just the ultrapower of S, right? But there is a strong infinity Borel code waiting for us in this ultrapower once we do it. Okay? All right. What does the last line say? It says, then A has a strong infinity Borel code contained in delta infinity S, and the code is definable from the original code S. Yeah. Okay. So, I mean, at best, we're going to be able to sketch this. There are a couple theorems along the way that, again, I don't want to take too much longer, but a couple theorems along the way that use similar machinery, which are sort of more realistic targets, and I will just state those quickly. So one requires a definition. So we're going to define for S and T contained in the ordinals, just S D below T. Just really, S is a weaker degree notion than T if the set of X, I guess now in the Cantor space it doesn't really matter, such that the reals intersect L of T and X are not contained in L of S and X. That's a hard bracket. Contains a Turing cone. Okay, so that's just an order on sets of ordinals. There's some name, there should be a name for giving a weird-looking, weak definition when a theorem will later make it make sense or something. Which is kind of, there's a theorem that makes this definition look more normal. So since I'm out of time, let me just jump right to the theorem. Okay. So here's one version of the theorem. So the theorem says, assuming Turing determinacy plus, what do I need literally? Turing determinacy plus DCR, I think. Plus every set is infinity Braille. Our set of this is contained in infinity Braille. Uniformization is equivalent to there being no maximal element in this order. Uniformization. So there being no D maximal element. I guess I could have stated it locally, one set at a time. But I didn't. I'll state it that way next time. The last theorem, the very first theorem in this sequence, I think, is just that the infinity Braille sets, that collection of infinity Braille sets is projectively closed. And again, that's assuming Turing determinacy, I think, plus DCR. I didn't even write it in this piece of paper. I think that's the theorem. Okay, so there's a sequence of theorems that analyze infinity Braille codes, looking at these ultrapowers, sometimes by the Turing degrees, sometimes by the S degrees for different S's, right? And, okay. So, well, these two theorems are getting, well, they're getting different things. They're all analyzing the ultrapowers, right? So this is, sorry, I'm going over. If we look at an infinity Braille code, it's not obvious that the infinity Braille codes are going to be projectively closed, right? If I have an infinity Braille code for a set of pairs, right, the projection operation is just over the wrong type. They just directly plug into infinity Braille definitions, right? But, okay, you can do it with the right determinacy assumption. So, okay, so this is, they're all ultrapower arguments and just of increasing complexity, I guess. So probably this is the first target, and then that one, and then sketching that one is the final goal, probably. But I haven't told you anything about the Vopenka algebra, so that's the first thing we will have to do on Thursday. So, okay, sorry I went over. Thank you. All right, thank you.